Thank you for the introduction, and thank you all for being here. This is a talk on multi-queue fair queuing, which is a scalable I/O scheduler for fast multi-queue devices. It's a collaboration with Shen from Google, Michael Scott from University of Rochester, and Marty from Google. In a conventional I/O space design, processes would submit their request to OS, which in a centralized I/O scheduler reorders and dispatches requests to guarantee properties like fairness. As I/O devices like network, storage, and accelerators become faster, reaching throughputs of millions of IOPS per second, and with the increase in the number of cores per package, the centralized scheduler cannot scale anymore. For a device supporting millions of IOPS per second, the scheduler needs to dispatch a new request at intervals less than a microsecond. The question is, what can you do in less than a microsecond? Assuming roughly 100 nanoseconds, for a remote cache miss, this is barely sufficient for 10 cross-socket coherence misses. With single core performance staying relatively flat and device speeds continuing to increase, serializing requests at these rates will only become harder and more challenging in the future. Due to these reasons, I/O design has moved toward multi-queue architecture in which each hardware thread owns a dedicated I/O queue directly exposed to the device. In this design, each thread communicates with the device independent of other threads, incurring no cross-CPU communication or cache coherence traffic. Linux's multi-queue block layer is one example of such shift, but you can see this pattern and this shift in data plane networking and also in accelerators. As a result, the I/O scheduler, which was responsible for providing fairness in the conventional I/O stack, has been completely eliminated from this design. So you don't get any fairness here. While coherence-free execution is fundamental to achieving good scalability and high throughput, it introduces new challenges in preserving system-wide properties. One such property is fairness, which is the focus of this work. It is not straightforward how to guarantee global fairness without global communication, which multi-queue I/O design aims to minimize. So how can we achieve fairness without totally negating the scalability offered by multi-queue I/O design? This is the main focus of this work, and in the next slide, we are going to show how to reconcile these two seemingly contradictory goals. For the rest of the talk, first we describe the high-level design of multi-queue fair queuing. Then we show how multi-queue fair queuing can be implemented using scalable data structures. Then we share experimental results basically employing multi-queue fair queuing to provide fairness for real-world applications. And finally, we conclude and discuss future directions. Among the existing notions of fairness, we chose to design our I/O scheduler based on the fair queuing class of algorithms. Fair queuing originates from network packet scheduling and has several desirable properties that makes it a prominent choice for implementing I/O schedulers. In particular, fair queuing algorithms support proportional share based on the weight of the flows. They are work conserving, meaning as long as you have requests in the system, the device is not going to be idle. They don't allow underutilizing tasks to accumulate their share and use it in a sudden burst, possibly causing significant latencies to other users. And finally, they provide fairness guarantees, provable fairness guarantees. In multi-queue fair queuing, we want to keep all of these properties, but we also need to support parallel dispatch to exploit the internal parallelism of modern devices, such as modern SSDs and accelerators. Specifically, we designed MQFQ based on an existing fair queuing algorithm called SFQD, or start time fair queuing with D-parallel dispatch. Roughly speaking, and there are details in the paper, upon arrival, a request gets a start tag, which is the accumulated resource usage of the task that submitted the request before we start servicing the request. The requests then are ordered by their start tag and dispatched up to depth 3 to allow for parallelism. Ordering requests based on this notion of start tag as opposed to the real arrival time guarantees that each time that we are dispatching, we are prioritizing the flow that has utilized the least amount of resource. But one might ask why we just use SFQD directly to provide fairness for multi-queue stacks. There are two main challenges that prevent SFQD from scaling for fast devices and many CPUs. So these are the challenges that multi-queue I/O resolves. First, strictly ordering requests in a centralized queue is a significant point of contention. And second, SFQD needs to track some global statistics, such as the number of in-flight requests, number of requests that has been dispatched but have not been completed, that if you don't do it properly, it can cause significant communication overhead in terms of coherence traffic. So this figure simplifies, but shows how SFQD is implemented. Requests are submitted by processes, they are assigned a start tag, and then sorted in a centralized queue to be dispatched in increasing order of start tag. There's no wonder this implementation, at least, is not going to scale. In modern systems, we need to do millions of DQs per second, and the central queue is maintained by a large number of competing threads. In multi-queue fair queuing, first we break this centralized queue to independent queues, each sorting local requests in increasing order of start tags. We could maintain the same semantic as SFQD if we dispatch the smallest request across all of these queues, but that serialization would basically negate any benefit that we would hope to get. Instead, and to enable a scalable implementation, we introduce a parameter T, which we call throttling threshold, that allows the dispatches from different queues to basically commute within a window of T. Basically, they can be dispatched out of order. Specifically, each queue, because it has an independent access to the multi-queue device, can proceed to dispatch a request as long as the start tag of that request is at most within the T of the smallest request in the system. A queue that finds itself violating this condition stops dispatching more requests, and it's going to be throttled until a later time when the slowest queue catches up and basically notifies the throttled queue to resume dispatch. We prove that this relaxation does not violate fairness. Specifically, we show that the difference in service received by any two flow or any two tasks is always bounded. And the bound is a function of the throttling threshold and the parallelism of the device. Please see the paper for the proof and the assumptions on the proof. While allowing dispatch to commute and to be reordered within this window does remove an important obstacle in scalability, we still need to maintain system-wide statistics that would inevitably cause coherence misses. In particular, multi-queue fair queuing needs to keep track of the slowest queue, and to achieve this, we use a scalable concurrent data structure. It's a lock-free data structure called mindicator. Also, multi-queue fair queuing needs to keep track of how many requests have been dispatched but not completed at any given point in time in order to prevent queue buildup in the device. This is achieved through another scalable lock-free data structure that we call token tree. We also need to track metadata required for unthrottling queues, which we leave out of this presentation in the interest of time. To give a high level, the big picture of how we implement multi-queue fair queuing. Multi-queue fair queuing's implementation relies on localizing synchronization as much as possible to achieve scalability. The main goal is to basically keep interactions at higher levels of memory hierarchy and avoid expensive coherence misses as much as possible. We prefer to synchronize between sibling hyperthreads before synchronizing at socket level and before modifying a globally accessed cache line. I'm going to give an example of how, in one instance of the lock-free data structures that we use, which is token tree. So as an example of how localizing synchronization in multi-queue fair queuing works, let's take a look at how we keep track of the number of in-flight requests. We introduce a tree-like data structure we call token tree, where the sum of values of all nodes represent unutilized parallelism, that is the available parallelism. When there is no in-flight request, or we can think at the beginning before we start, it can be thought of to have D tokens in the root node. When a queue needs to dispatch a request, it borrows tokens from its parent going upward toward the root. If no token is available, like in this example for CPU 2 and CPU 5, the queue needs to be throttled. When a queue, say, for example, here for CPU 0, has a request completed, it will have an additional token to be used. Let's assume CPU 0 doesn't want to reuse this token because it doesn't have any other request to dispatch. Then it has to unthrottle either CPU 2 or CPU 5. To localize interaction, it would decide to unthrottle CPU 2. It will return the available token to their least common ancestor and node and send an intra-process interrupt to unthrottle CPU 2. Note that this choice reduces the latency of the notification, but it also passes the token in the last level cache of the socket 0 without causing cross-socket coherence misses. Now that we have an idea about how multi-queue fair queuing is designed and implemented, let's see how it performs in practice. In order to evaluate the fairness and scalability of multi-queue fair queuing, we implemented it as Linux I/O scheduler for multi-queue block layer. We benchmarked multi-queue fair queuing over an NVMe SSD capable of 500,000 IOPS per second, and an NVMe over RDMA capable of nearly 4 million IOPS per second. We use flexible I/O benchmark to create workloads that we know its characteristics, such as I/O depth, concurrency, size. And we also use Aerospike key value store configured to respond all of the requests from the storage, and FlashX graph processing framework, which can do graph computation on large graphs that don't fit in the main memory. We compare multi-queue fair queuing against budget fair queuing, which is the available proportional share scheduler for multi-queue block layer on Linux. BFQ does not support parallel dispatch, and it stores all of the requests in a central queue before dispatching. Therefore, there's a scalability limitation for BFQ. Let's look at multi-queue fair queuing applied for fairness in real applications. On the left, the blue bar shows the PageRank algorithm on FlashX graph processing framework, and on the right, we have Aerospike key value store benchmark with YCSP. The orange bars in both cases are flexible I/O benchmark, is a synthetic benchmark as an antagonist process that can saturate the device all by itself. The x-axis shows the slowdown of each of the applications compared to when we run them alone. A 2x slowdown, because we assume that the processes have the same weight, a 2x slowdown is a fair slowdown in this situation. When no scheduler is employed, you can see that both FlashX on the left and Aerospike on the right have more than 4x slowdown, while the synthetic benchmark barely experiences any slowdown. Multi-queue fair queuing in both cases can balance the slowdown. Regarding BFQ, since it does not support parallel dispatch, it cannot accommodate applications with high parallelism, which is, in this case, synthetic benchmark and Aerospike. Here we show the scalability results for multi-queue fair queuing. The benchmark is on NVMe over RDMA, capable of sustaining 4 million IOPS per second when there is no contention. This is the case with the blue line here. The network link is saturated at around 17 CPUs, 17 threads here. The orange line shows how multi-queue fair queuing scales almost linearly up to 16 CPUs before we start using the second hyperthread. And it reaches up to 3.1 million IOPS per second while providing fairness. Recall that the blue line does not guarantee fairness. Lastly, the green line is Linux BFQ, which does not scale because it reorders requests using a centralized lock-protected queue. BFQ is a good showcase of naively applying fair queuing algorithm to multi-queue I/O stack without addressing its scalability problems. To conclude, we discussed a major consideration when moving to multi-queue I/O designs. While they achieve scalability, due to coherence-free execution, properties like fairness being global are hard to achieve without incurring coherence traffic. We show that it is possible to achieve even a strong fairness guarantee like fair queuing without negating the scalability of multi-queue designs. We introduce multi-queue fair queuing and the scalable implementation of it that borrows from techniques used in design of scalable data structures to achieve throughputs of more than 3 million IOPS per second, while at the same time providing fairness. And with that, I would be happy to take any questions.
Irfan Ahmed, Magnesian. Good improvement on existing work, especially relating to scalability. I noticed that you're using interprocessor interrupts as a fundamental latency control mechanism. In my previous work, I've noticed and spent actually considerable energy trying to minimize interprocessor interrupts. Did you evaluate the impact of the interprocessor interrupts on actual useful CPU work that's happening during these I/O patterns? I didn't see that in your paper. I wonder if you have any intuition around the impact of that. And how sensitive is your performance, are your performance results to being forced to do IPIs for every single escalation?
So you're not going to do IPI for every single request. It's basically when a queue is you need to unthrottle a queue and you need to do an IPI. But yes, IPI is going to happen, frequently, and so we have a comparison in the paper that we compare using IPI with doing polling, and with respect to CPU utilization, we realized that it's better to do IPI. There was another part of the question that I guess I didn't understand, if you repeat it for me.
Yeah, for example, how sensitive is the throughput results that you show to the frequency of the IPI? Like if you were not to do an IPI, if you skipped an IPI, right, you only did every other as IPI, like what's the sensitivity? Do you see what I'm saying? Like, because for a real compute workload, right, where computation is happening, IPIs will destroy a whole bunch of L1 locality, L2 locality. Like if you try this with any like database workload that actually is doing some join in the background, IPIs will destroy workload performance.
So we have a compute sensitive workload, which is the graph processing application. It doesn't seem to suffer from this issue. Okay. So the reason I think is that the IPIs are not maybe as frequent as you think them to be, because basically when you need to unthrottle a queue, you would need an IP
per process.
Yes. But what we are really trying to reach fairness for is for C group. So we get the C group and we try to, based on the weight of C group, we assign the start tags.
As a result, the token availability is per C group.
Yes.
Okay,
yeah.
thanks.
Thank you.
So if there's no more questions, I've got one question I'd like to ask maybe while our next speaker sets up. Which is, did you explore the sensitivity to the parameter T that you have, which looks at, I guess, bounding how much unfairness you have?
Yes.
How do your results vary, and how would you go about choosing T in practice?
So in the paper, we explain exactly how we choose T. It's basically we assume the worst workload, which is extremely parallel with respect to the size of the machine workload, and submitting very small requests. So this is the worst case workload, and we try to match the basically the raw device throughput by assigning a T. Any other workload in that machine is going to need a T smaller than that particular T. So it's a combination of how fast the device is and also how the characteristic of the workload itself.
So thank you, and let's thank our speaker one more time.